Hi everybody, welcome to another Chats with Chaudhry. I hope you're safe and well. Today I've not just got one expert, not two, but I've got three experts here with me today to talk about the complexities of the vaccine supply chain and how glass vial testing is an important, maybe not so glamorous, but important step in the process. And I'm joined today by Josh Truswell, Scientist 1, Pharmaceutical Chemistry, Nikki Alton, Senior Scientist 1, Microscopy Lab. I got it right, Nikki. There you go. And Alan Cross, Senior Scientist 1, Metal Labs. So, how are all of you?
Yeah, doing quite well, thank you.
Well, right. So, before we start, can someone please give me a quick overview of Rssl? And then, if you don't mind, if I can just get a quick background of your sort of academic experiences, if you like. Alan, would you like to start?
Yeah, I'll pick this up.
Thank you.
So a little bit about Rssl. So Reading Scientific Services Limited, based in Reading, up on the university campus. And we provide contract analytical services for the pharmaceutical industry. So we work with the big names and smaller names and all sorts of people covering a wide range of aspects of pharmaceutical analysis. So this is from method development, QC, raw material testing. We have a range of laboratories, so from wet chemistry to high-end analytical equipment to do problem solving and routine analysis, QA, release. So we cover the whole range. We're quite a diverse company, and obviously we have a huge range of experience. My experience, so I'm an Exeter University graduate. Did chemistry when they did have a chemistry department. I've been in been an analytical chemist for 21 years doing metals analysis. So that's spectroscopy, ICP-MS, ICP-OES, and AA. So yeah, but just been doing pretty much that for 20 odd years. Originally in the Environment Agency, so environmental samples, and now working on pharmaceutical and food analysis.
Fantastic, thanks, Helen. Nikki, what about you?
Yes, so I come from quite an academic background, and I did a lot of forensic analysis, forensic research, and fingerprint chemistry in the past, and I moved over to Rssl 6 years ago now. So I've been with the microscopy team for 6 years and counting, and I'm one of the analysts there, and I used to be quite heavily involved with the vial testing, and now I'm doing more method development studies and increasing service offerings within the lab.
Fantastic. And Josh, last but not least.
Yeah, so I actually went to Reading Uni to study chemistry. So graduated from there, and over the past 4 years have done various worked in a couple of different chemistry companies, from manufacturing to now doing more analytical wet chemistry stuff. But I'm directly involved with all of the glass vials testing that goes on within the wet chem department. So it's a very regular occurrence for me. So yeah, really glad to be part of this.
Fantastic. So a really basic fundamental question to start with. So how does Rssl support in the vaccine supply chain and manufacturing? Who'd like to answer that?
I don't mind taking that.
Cool.
So it's kind of moving on from what Alan had said previous. So there's such a diverse range of labs that we have within here. So I'd say the three of us that are here today, microscopy, metals, and pharma chemistry in general, can aid with the glass vial testing that we do. There's extractables and leachables from how our glass vials are going to interact with the vaccine or the solution that is meant to go into it, along with the rubber stoppers or the sealing mechanism that is used to crimp with the vial.
Yep.
But we also have a range of buffer analysis, biomolecular analysis, and physical sciences also do a lot of penetrability and fragmentation to do specifically with the rubber stoppers that we used. So I think there's a huge scope for what Rssl can support within the glass vials / rubber stopper analysis, and it's much larger than just what we're putting into the vials. It's making sure that the raw material vial and stopper system that you have is robust enough as much as the vaccine is that's going into it.
Right, fantastic. So how does the pharmaceutical wet chemistry lab aid glass vial manufacture?
We specifically, in terms of looking at the glass vial, so we can assess the type of glass vial. So there are 3 different types, which I'll explain. But within the pharmaceutical basis, we can assess the type of glass. We can assess whether there's heavy metals present, along with metals. Alan will speak about that later. Along to the sealing properties that the rubber stoppers have, as well as spectral transmission. If you've got coloured glass,
Right.
sometimes light sensitive compounds need colour glass. We can do spectral transmission analysis to assess that, and this is to all ranges of pharmacopoeias from European, United States, Japanese pharmacopoeias, and along with that there's turnaround times. So obviously COVID related, we have an ERS, emergency response system, that allows us to, if it is COVID related or something that is an emergency, we can look at different turnaround times to suit clients that need it.
Fantastic. And how do you assess the different types of glass vials?
So there are 3 different types. These are mainly used within the pharma industry. So we've got type 1 glass. This is neutral or borosilicate glass. It's suitable for most preparations within the pharmaceutical industry, for parenteral use or not. We've got then type 2, which is a lower standard of glass. It's just soda lime glass, but it's coated with a layer on the internal surface that will have high hydrolytic resistance. This sort of inhibits the leaching of alkali metals into the vaccine.
Right.
So this the soda lime has quite high amounts of sodium oxide. This will over time leach into the liquid that's housing it. And then along with this, so there's a high hydrolytic resistant surface for our type 2, and the type 3 then doesn't have any surface coating on it. So we can assess the different types of vials, yep, using 3 different tests. So with the European Pharmacopoeia sets it out quite nicely. There's 3 different tests that we can run. So test A is our surface hydrolytic resistance test. This is essentially filling the vials with water.
Right.
We then, from that, put them under a large amount of stress. So this process involves autoclaving. Basically, there's a load of, the autoclave is a very large kettle in a strange way. So we bring the vials up from room temperature to 100 degrees. And then by closing off the system, steam is produced, the pressure increases, and we're actually able to get water to be a liquid at 121 degrees Celsius.
Right.
This is the sterilization process. For the surface hydrolytic resistance, we keep it there for about 60 minutes. And then from that, this sterilization process is accelerating the stress on our vials, which accelerates the leaching process from the surface into the water that we've placed in it. So at the end, it's a simple acid-based titration. We're then seeing how much alkali has leached into our water by titrating it with acid. Right. This is shadowed quite closely with our test 2. So the surface hydrolytic resistance that we just did was to differentiate between type 1 and type 2 from type 3 glass.
Right, okay.
And then our test B is hydrolytic resistance. We then crush the sample, forming small glass grains. This will obviously differentiate between the surface coated type 2 glass and the borosilicate type 1 glass, because we're shattering, which gives a whole overview of the entire surface of the glass rather than the coated internals. This again, it goes through the same process as our surface hydrolytic resistance with an acid-base titration at the end, and allows us to differentiate between type 1 from type 2 and 3 glass.
Right.
So, and then there's a final test which is quite alike that test in terms of being able to differentiate between type 1 from type 2 and 3 glass, which is a glass etching test.
Right.
And it's essentially adding a mixture of hydrofluoric acid and hydrochloric acid to our samples, which etches and takes away the first few layers of your glass, delaminates the glass, and again will etch away any of that high hydrolytic resistance layer coating the inside, and allows us to differentiate then with an acid-base titration between our type 1 to type 2 and 3 glass.
Great. Thanks for a very thorough explanation. Actually, I now far better. No. It's great because, as I said, you always hear the top line things that we do tests, but you don't understand the process, and that's been a really thorough explanation. So thank you for that. I know it's different labs to you guys, but have you got anything to add to that, Nikki or Alan?
No, I think Josh has covered everything.
Yeah, I actually learned a little bit more about it today myself. So
excellent. Well, that's the point of these interviews, to make education for everybody who's watching. So that's great. So, do you have any case studies though where the vials have been flagged up in the raw material testing, and how you've been able to help clients troubleshoot and understand the reason for this?
Absolutely. So this has been an ongoing issue in the past. So we have a client that that comes to us that specifically they actually have the raw glass canes, and they actually press them and blow the glass in-house to make the glass vials. And they have internal procedures as to washing after this pressing process and blowing process. They internally wash the glass and send it to us. And we do find after one wash, sometimes it's type 1 glass, but it will fail and not conform to the surface hydrolytic resistance specification laid out. So sometimes we actually have to find that they then have to wash their batch multiple times, double, quadruple times, to ensure that that when it comes to Rssl and we process the surface hydrolytic resistance testing, that it conforms to specification. This can be to a number of reasons. We presume it's because when the glass is blown in the little mold, there's a small rod that goes in to blow the glass. We believe this rod might be coated with some sort of resistant coating to stop it sticking. This coating then gets aspirated inside the vial, and if there's not enough washing steps before arriving to Rssl, it may cause either it's a slightly alkaline solution, which means that it will fail the acid-base titration, or that it has some sort of other reaction within the glass. So yeah, that's been a really interesting case study.
Cool, fantastic. So now we're going to move to another test, and I think this is related to you, Alan. So I know the pharmacopoeias talk about another test for glass vial testing. So how does your metal lab support that? And does the metal lab work closely with the pharmaceutical chemistry team for the testing?
Yeah, so where we get involved with the vial testing is the test for arsenic.
Right.
So anyone who works with pharmacopoeias know that every pharmacopoeia has its own way of doing things. So I think the USP has a wet chemistry test, which is a colorimetric test, but for the EP, they use atomic absorption spectroscopy to assess for arsenic. Right. The reason they do this is salts, typically arsenic trioxide, is used as a modifier in the glass vials, so it improves opacity and some of the properties. Obviously, you don't want to be have that coming into a drug product, especially if it's a parenteral. So we test for that. So in a lot of cases, if the vial's being tested for surface hydrolytic resistance, we work with the pharmaceutical team to take the solution S, as they call it. We can, they will do the titration on that with the acid base, and we'll take some of that solution. We then add hydrochloric acid, quite a high concentration, potassium iodide, and this is a reducing agent, which allows the arsenic to be measured in the system. So it's pushing all the arsenic into the right form, which can then react with sodium borohydride, which generates arsine gas, so which is arsenic trihydride, and that can be detected by the AA. So that's the test we do with that. Unfortunately, if the arsenic is required on a sample that is glass grains, we then have to do the same preparation as you do for vials, as the glass grain is all consumed during their testing. So we have to kind of then autoclave the samples, perform the same test, but just to perform the arsenic on that solution.
Right. Okay. So how does Hydride AAS used for arsenic testing differ from routine flame AAS testing, and why is it employed?
So flame AAS, or AA as a basic technique, so you have a lamp of a assigned element,
right?
And if atoms in the ground state enter the beam of light, the signal is reduced because they absorb the energy, and that reduction in energy is measured.
Right.
So typically with flame A, you aspirate a sample, it releases those atoms, you measure it, and your detection limits are typically ppm level,
right?
Which is fine for things like sodium. You know, that's more than sensitive enough. For something like arsenic, your levels, its toxicity is at very low levels, so you'd be more interested in the ppb range. So Hydride is a clever way of improving the sensitivity for those elements. So you're producing a chemical reaction to generate arsenic gas, so that can concentrate the sample. So rather than a mil a minute flowing into a flame, you can take 100 mils of sample, react it, and then all of the arsenic comes off.
Right.
And then that goes into a heated furnace, and that causes the hydride to dissociate, and you're left with the arsenic-free atoms, which can be detected. So the specified calibration in the EP monograph is 5, 10, and 15 ppb, and that actually gives a massive signal, so you can get really sensitive analysis. So if there is any arsenic there, you can detect its really low levels. But obviously this kind of setup isn't standard, so a lot of labs that have AA won't necessarily have the hydride generation.
Right.
So.
All right. And what other applications of Hydride AAS are there, and how else have the metals team helped with sort of COVID-related projects?
Yeah, so arsenic and so hydride only works on a limited range of elements. The chemistry has to be correct. So the Japanese pharmacopoeia, they do some tests with mercury in raw materials, so hydrochloric acid and sodium hydroxide. Are both analyzed to mercury. Very similar process. It's generating, in that case, you generate mercury atoms. They're gaseous and they can react in the same way. Some of the other ways we supported with the COVID effort is looking at buffers, so ensuring that the correct buffers are used in vaccines. So sodium, potassium, calcium, magnesium. Right. They're typically tested by AA. We've also been involved in the extractables and leachables, so ensuring that there's no elemental impurities entering the drug products.
Sure.
Yeah.
And Nikki, Josh, anything to add?
No.
you guys are too thorough when you do these explanations. No one can add anything in. Right, so Nikki, over to you now. So what do manufacturers do if they identify an increased number of rejects during post-production? And when they do their QA/QC screening process before release, so what do they do?
Well, generally when this happens, the manufacturer is aware of a more problematic issue, and it could be a serious contamination within the batch. So a pharma client would come to us with the problem and highlight that it is an urgent situation. So what we would do is we would look at the vials, a large number of vials. We would kind of look at them, screen them and triage them as a preliminary investigation and indicate the possible source of contamination without actually having to isolate the foreign material within the vial. So it's a very time-saving process, and obviously we would only be able to give an indication of the identity, but we would be able to see if there are any commonalities within the contamination within all these vials. And based on past experiences and some databases of foreign material, which sometimes are customer specific, we can find or indicate what the source of contamination could be. So it's quite a speedy process, so to speak.
So it's like the CSI of pharma, basically, hence the forensic background.
Yes, I did say I came from a forensic background, so this really fits in with my my education.
Right. So, and what is the process involved in identifying contaminants and sourcing the issue in your lab?
Yeah, so we would generally always start with a preliminary investigation. So we would screen the vials and look at the foreign material within them and communicate with the client if there are several particles in there, and see whether they were just interested in the one particle that they'd previously identified or whether they'd want more analysed. And also screening means that we can look at characteristics like the size, the shape and the colour. So once we open the vial and we isolate the particle, we know it's the same particle, because there is the possibility of the particle being lost, not just because, I mean, we're very good at what we do. I don't need to blow my own trumpet, but sometimes the particle can be extremely static, or it could be intrinsic contamination. So when I say contamination, it's not actually contamination, it's actually part of the formulation itself, and as soon as you open the vial, the particle goes back into solution. So we would want to record as much information as we can before we actually open the vial. So once we've isolated the particle, we would then proceed to analyze it, and we would use a series of techniques, starting from the basics like microscopy and staining if required. Then we would go into compositional analysis, and we do for a transfrared spectroscopy, confocal microscopy. And then we could do some electron microscopy as well, and follow that up with X-ray microanalysis to look at the elements present. We also have a extensive database, so we would be able to identify the particle. And it's very important for us to be able to tell the client what the composition of the material is, because then we'd be able to go back to them and tell them, well, with them, kind of try to identify where the particle might have come from. So we would communicate with the customer very regularly, and we could prepare things like toxicological reports if required.
Right.
Sometimes the contamination can also be intrinsic to the vial, so it could be a vial imperfection, and we have the ability to image this non-destructively using our X-ray microtomography unit. So a lot of complicated, astounding instruments that we've got in the microscopy lab.
And I'm glad you pronounced them rather than I'm pronouncing them, so I've got them right on my tongue. So that'll be fine. So I mean, have you got any examples of common issues that do come up?
Yes, so some very common examples include stoppers. So sometimes the manufacturer changes the stopper supplier, and without the manufacturer knowing, the stoppers can be associated with fibers, and so they would see an increased number of particles within the solution contained within the vial. So what we would do is we would obviously take some of these vials and also have a bag of the stopper, and we would find commonalities between the fibers within the vials and the fibers associated with the stoppers, and we could tell, we could identify the source of that being the stoppers and the manufacturers were the stoppers. And another quite common situation that we see is machinery wear debris. That sort of contamination can be introduced at any point during the manufacturing process, and it generally presents itself as dark marks on, for example, the stopper itself, and we are able to analyze these in situ. So first we would look at the stoppers under a light microscope, and we sometimes can see these dark particles, and sometimes they can actually be reflective. And then we would take the entire stopper and mount it under an electron microscope, and there'd be a difference in the elemental backscatter of these particles because of the difference in the atomic mass. And then we proceed to looking at the elements present, and we generally see things like iron in there, if it's steel, or other elements characteristic of other metals, and we could work with the client to see whereabouts these particles could have been introduced in the manufacturing process. So root cause analysis, basically.
Fantastic. Well, thank you very much to all three of you for giving me such a thorough overview of your particular test that you do in your labs. I mean, it's been really fascinating, actually. I'm not just saying that genuinely. You don't realize how much work goes into it and how interesting it is. It is, as I said, investigative work, but non-crime related, obviously, hopefully. So it's really interesting to hear about that. Where can people get more information if they want to know more about the different techniques, applications and works that Rssl discussed today?
Well, I can take that one, guys. So we have got lots of resources, mainly the website, LinkedIn. We've got a Facebook page as well. So we've got a very good customer services team, which and they can help with any inquiries if required. So.
Fantastic. So I'll put the links above the video. So what I'd say is that I hope everybody found that really interesting. I certainly did. If you'd like to know more about how you test files, then please check out the Rssl website. As you can see, they've got experts here to help you, as you've known. So all that stuff is Nikki, Alan, Josh, thank you very much for taking time out to talk to me today. It's been really, really interesting. And I hope you have a fantastic 2021. I know we're into February, but I still feel I can say that was everybody's in lockdown. So have a fantastic 2021 and stay well and stay safe. So thank you very much for your time today.
Thank you to yourself, Rssl. Thank you for having us, for hosting us.
No, it's lovely to meet you all as well. And I hope you all found that useful. As I said, check out the links above the video. If you've got any questions for Nikki, Alan and Josh, I'm sure they'll be delighted to answer them. So if you watch it and you've got some questions, please feel free to put them in the comments below the video, or you can also message them directly. I'm sure they'll be happy to answer your questions. They're all on LinkedIn. So until next time, as always, stay well and stay safe. Bye-bye.